The second thing we want to look at when we consider the atmosphere is not its temperature, but its movement, or what we commonly call wind.
First, let's look at rule number 3. That is to say, warm air is lighter than cold air. This is obvious to anyone who's ever struck a match, because when you strike a match, the flame always burns up. When you look at the flame of the match, what you're really seeing is superheated gases heated by the combustion of the match. And because these gases are very hot, they are light and therefore burn up. They rise, they float. The flame never burns down. That's because hot gases are lighter than cold gases. In this slide, we see the implications of this for the motion of wind on the Earth's surface. In this slide, we see a shaft of cold air at the right and of relatively warmer air at the left. The cold air at the right, indicated by the blue arrow, is relatively heavy, and as a consequence, it produces what we call a high pressure. The heavy cold air pushes down toward the surface of the Earth. At the left is a relatively warmer center of air, indicated by the red arrow. Because this warmer air is light, it tends to rise or produce what we call a low pressure zone. Between the high pressure zone and the low pressure zone is a wind that blows from the high pressure on the right toward the low pressure on the left. In other words, air moves because of the unequal heat or temperature of the air. Moreover, this occurs on a global scale. This slide shows the Earth on its side, the axis of the Earth running horizontally between the North Pole on the left and the South Pole on the right. We've put the Earth in this position so that you can observe the motion of air above the Earth's horizon. In part 1, we looked at 2 rules, that is to say, that the sun heats the Earth unevenly, it's warmest at the equator and colder toward the poles, and secondly, that the Earth heats the air correspondingly unevenly, that the Earth heats the air more near the equator than it does toward the poles. These facts account for much of the movement of the air or atmosphere above the Earth. In this slide, we see that the air above the equator is warm, therefore it's light, therefore it rises, while the air closer to the poles is colder, therefore heavy, therefore it falls or pushes down in a high pressure zone. This moves air from either extreme toward the equator, in the northern hemisphere, from the north toward the equator, in the southern hemisphere, from the south toward the equator. As the air above the equator rises, it is pushed up and outward by air coming in from behind. And this rising air is cooled, first because it is higher in altitude or further from the surface of the Earth, and as we said, altitude matters. The further it is from its heat source, the colder it gets, and also because it's being pushed toward the poles, and the poles are of course colder. Now something very surprising happens, and this surprise explains much of the motion of global wind patterns. As the air rising from the equator is pushed poleward, it builds up in an extremely cold shaft of air at approximately 30 degrees latitude in both the northern and southern hemispheres. The buildup of this extremely cold, heavy air creates a high pressure zone, which pushes down toward the Earth with great force, forming what we call the subtropical high at both 30 degrees north and 30 degrees south. As this tremendous high pressure zone pushes down toward the Earth, it forces the air on the surface of the Earth outward, both north and south. The cycle of air produced between 30 degrees latitude and the equator therefore creates a cycle or cell, which we call the Hadley cell, named after George Hadley, the 18th century English scientist who came up with the early explanation of global wind patterns. Pay special attention to the subtropical high and its effect on air movement or wind at the surface of the Earth, because that will explain much of the global wind patterns.